Okay, good afternoon. We start the lecture. For the last few lectures, we talked about the three 2D NMR techniques in detail. One is cozy. It tells you which proton coupled to which proton in an easy way. The second technique we are talking about, we have to talk about is the HMQC. HMQC can help you to find which proton is on which carbon, right? You can, after you sign the proton NMR, you can use HMQC to readily find, to assign the carbon signal. And then the third one we talk about in detail is HMBC. HMBC just tells you J2 bond and 3 bond CH correlation. But you didn't see 1 bond correlation. But for sometimes you do see this. Because in that case, it's a satellite peak. Now by this, anybody can tell what's the very obvious difference between HMQC and HMBC. The difference. Unless you know the difference, then you know how to use it. For example, I give you 2 spectra. Both are CH correlation. Can you tell which one is HMQC, which one is HMBC? Should be, right? Because for HMQC, along the proton dimension, if you pick up 1 proton, you draw 1 line, it can only have 1 spot. Because 1 proton can only on 1 carbon, it cannot be on 2 carbons, right? But for HMBC, for 1 proton, you draw 1 line, you can see up to how many? How many? How many? Can you count? 12. Is it 12? Maximum is 12. Right? Because 1 carbon, for example, you just assume you see that instead of on 1 carbon, you see 3 more carbons. On each more carbon, you have 1 more layer. That's another 3 carbon. That means you see 3 direction. For each direction, there is a third-butyl group, for example. That's the maximum. That's this molecule, for example. Of course, this cannot be all methyl. Like this one is Me3, Me2, or C2Me, like this. The other one is different, it's CH2OH or CH2 chloride. The other one is CH2 bromide. Then you have another one, it's even weird, it's like aldehyde. The other one is ether. Then the other one is, for example, amide. This is very special compound. It doesn't exist actually. And this proton can see 12 carbons. Like first layer 1, 2, 3. right? The second layer, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, actually, even though this molecule doesn't exist, it does help you to visualize how to look at the HMBC peaks, right? This is the difference. You know, sometimes students ask me, why you didn't label HMBC and HMQC? I cannot tell which one is which. Better not ask this question, right? Okay, after we finish HMBC, yes, HMBC can help you to put fragments together. That show more information on connectivity. Later on, when we show application of those 2D techniques, then I can give you more detailed information on how to apply those 2D techniques. There is one more technique, 2D technique, that is frequently used by organic chemists. That one is NOE, N-O-E, 2D NOE experiment. NOE, it's not coupling through bond, it's coupling through space, right? It's dipolar coupling. NOE experiment give you information about the stereochemistry. It can tell in an easy way that tells you which two protons are close to each other in 3D dimension, right? That's why for NOE experiments, it's very useful to determining the radioisomer or stereoisomer, which one is which. Now this is overall, this is NOE spectrum, and in general we mention NOE spectrum. It's proton-proton NOE. That tells you which two protons are close in terms of space. For the NOE spectrum, and you have a positive peak and negative peak. But for NOEs in general, it's negative peak. It's red if the spectrum was printed in black and red type. And all the NOE related limitations, they have those NOE spectrum also have. For example, for NOE spectrum, we talked about NOE before, NOE effects. For small molecules, like molecule mass that's less than around 7 to 800, they show positive NOE effect. But for large molecules with molecule weight above 12 to 1300, they show negative NOE effect. But that negative NOE effect has nothing to do with the negative peak. Those two negatives are different. For the molecules with medium size, in that case, they don't have NOE effect. You cannot analyze through this NOE experiment. But now this is overall how the NOE experiment, NOE spectrum looks like. There are more and more information than Cozy spectrum. For Cozy spectrum, it's through bond correlation, and but for NOE, it's through space. Through space, that also includes, when we say two protons are close to themselves, they show NOE effect. In that case, they can through bonds, they can also be close. Like for monosubstitute phenyl ring, and the meta position and the para position, they are close to each other. It's J3, but those two are also close in space, like those. They are J3, but they are also close in space. That's why for NOE spectrum, you can find the most cross peak of cozy. Now I just use a few examples to show you how useful nosy spectrum is. Now for example, we have two isomers, like this molecule and this molecule. I get those spectrum from Singapore HSA, Health Science Authority, and they ask us to tell which isomer is which, because sometimes they have some drugs from human extraction, human bloods, and they don't know, just different radioisomer, they can have different effects. Some are drugs, some are not drugs, but some are allowed, some are not. You know, once they say they take blood from somebody, they use drugs, that kind of illegal drugs, and they want to sue them, and you need to provide evidence why you can tell it's an illegal drug. Then in that case, that's return help to us for spectroscopic analysis. In that case, I just choose a few examples, and that's the NMR training I gave them last year, so I use those slides also. Like for those two molecules, and they provide two sets of spectrum, like two sets of proton. Like one set is like this. The other one is like this. Two sets. You see the difference? This part may not too much difference. The different part is those parts. Especially when you look at those 3 sp2ch, this is 3 sp2ch. One spectrum looks like this. This is a triplet, this is two doublets squeezed together. One proton, two proton. The other one is doublet, doublet, and a triplet. Because based on those, two doublets, one triplet. Two doublets, one triplet. This is doublet, doublet, triplet. Doublet, doublet, triplet. You cannot tell. From the proton NMR, you cannot tell which one is which. Right? But we have to find it out which one is which. In this case, nosy is the most simple way to find it out. You know, now we do analysis. You know, when we want to find out, when we want to use nosy spectrum, there are so many spots there. You want to find the spots that can help you to solve the problem, right? You know, before we do further analysis, we just briefly sign those 1D NMR, 1D proton NMR. For example, for this one, from the integration, you see this is two proton, they are triplet, triplet. In this case, it's one of this one above 4 ppm, that should be the one CH2 next to oxygen, right? For both molecules, we just, this one can be either this or this, right? Now for these two protons, they are either this one or this, because this one is benzylic. It's around 3 ppm. Now this is, we know where is this one come from, where is this one come from. Now we have another one is this too little one. Too little one we can say is one of this distereotopic proton pairs, because this one is a chiral center, this is a chiral center. In this case, this CH2 is distereotopic proton pair, this is a distereotopic proton pair. Now you see these two little ones are two protons from this benzylic CH2. And now this one is methyl group. It's it's here, right? It's a doublet, you see, a doublet. That's because it's coupled to this proton. Now we know this one, this one, this one, and this one. And for this 3 we know is aromatic one. The 2 doublets come from either this, or this, or this one, or this one. The triplet is this one, or this one, right? This broad one is the amine, because amine, as I mentioned to you guys before, it can be anywhere, because in solvent, there are some water, they show exchange. They are broad and it can be anywhere in the spectrum. But this one, you may say, what's this huge one? That one is water, or DMSO. This one is DMSO. DMSO is always salt, is wet. That's why you see huge peak. Sometimes you have jittery warning site, you see huge peak. But you may say there are still something missing. Anybody can tell me what is missing? We're missing one thing. This CH, or this CH, is beneath here. And this CH next to a nitrogen is around 3.2. Then it's underneath this solvent peak. You see, this one and this one belong to this methylene group. These 2 little ones belong to this or this. Now we want to find out, for example, either this or this, which one it belong to which radioisomer. Then we do analysis. Like if, we always assume, if the spectrum for this molecule, we will see this CH2 will be close to this CH, right? Now in notice spectrum, we should see correlation peak of this CH2, that is this, with this CH. Where is this CH? This, either this one or this one doublet, right? Or this CH2, that's 2 little ones, with this proton, you should see correlation, right? If it's this molecule. If it is this molecule radioisomer, you will see this CH2, that's this one, should see correlation with this CH2 because they are close, right? Or this CH2 that's here, they can show correlation with this methyl group here. Because this single bond can rotate, it can bring this methyl close to this CH2, right? This is what do you expect? At least normally when I do 2D NMR analysis, I don't look at the spectrum first, especially for nosy. I just, in my mind, I expect something to, if I find some information, I can confirm if this is this isomer. But if you cannot say in this way, if I didn't find this correlation, I can say that's this molecule. Don't say in this way. For spectroscopy analysis, always do analysis with the spots, with the signal you can see. Never say with something you cannot see. Okay, now after analysis, we try to look at this CH2 that's here, the correlation either with one of these 2 doublets of sp2CH or with this 2 little benzylic CH. If those 2 has correlation, if this peak and those 2 little ones, they have correlation, that's this molecule, right? If these 2 little ones, this one or this one, has correlation with one of these doublets, or these two little ones has with one of this little one, and this small triplet, that's this one, also have correlation with one of the other doublets. You come from this one, right? Because these two show correlation, these two show correlation. But now for those two doublets, you don't know which one is which one. That means if this one has correlation with one doublet, that means these two little ones, these two little peak will show correlation with the other doublet, not with the same doublet. They should show correlation with different doublets. That's the analysis. Now we look at the spectrum. For example, for this one is this spectrum, the first one. The two doublets overlap somewhere here, very close to each other. You see this one here? This one is ethereal CH2. This one is this benzylic CH2. These two little ones are this. Now you see, for this CH2 here, is this one, you draw one line, it goes to this diagonal, right? And for these two little ones, is this one or this one? This or this? One is here, the other one is here, right? Now you see one spot. It's this CH2, show one spot with this little CH. Here, this little CH, and this CH2 is here. That means this one and this, the two protons in the deep pink circle, they show correlation. Now for this molecule or this molecule, they show correlation, that's this one. Actually, this CH2 here show correlation with those two CH, right? That's this two CH. One is in the circle, the other one is here. Now you find what you have. You can clearly see this is two spots. That means this CH2 has correlation with this distereotopic proton pair, right? That means this CH2 and this CH2 are close in terms of space, right? Now for this radioisomer and this radioisomer, the lower one, this and this, they are close. That means this spectrum belongs to this radioisomer, right? That's why, like in court, if the lawyer asks you to present evidence, why you think it's this one, not this one? You just show them this spectrum. This spot tells everything. Of course, you can find other information. You know, for example, if for this molecule, this CH2 is here, they shouldn't show correlation with either this or this because they are far away, right? You see, this one is a CH2, you draw one line, and for this, either this doublets or this doublets is here, you draw one more line. Now you see, for this cross, this is CH2 and this one of the doublets, here in this green circle, there is no correlation. In this case, this one and this doublets and this, all these doublets, they shouldn't have any correlation. Right? It further confirms this. But you cannot tell, I didn't find this correlation, I say it's this molecule. This is kind of a minor evidence, but not the major evidence. Major evidence is the one you see a spot. This spot here can clearly tell is this molecule. But here, there is no cross-pick here that can help you to confirm it's this. But it's not a major evidence. Right? Now you know what I mean. Confirm the structure with what you can see, what you can find with the spectrum. The one you cannot find is not evidence. It's just can, add additional minor evidence, not a major one. Now we can see this spectrum is this radioisomer. Because you see this CH2 and this CH2, you see the correlation. It's this inside this deep purple circle. You see this spots, it's this and this correlation. Now we look at the other one. Now the other spectrum is, here is a doublet, here is a doublet, here is a triplet. This triplet belongs to this CH2. This two little peak belong to this CH2. Now you look at this. This is you see these three lines, you draw three lines along this CH2, or this CH and this CH. Here is the CH2, here is the 2CH. You draw lines. Now you find for this CH2 has no correlation with this two distereotopic CH proton pair, right? On this circle, there is no cross peak. Not like in this one, you see two dots here, right? But for this molecule, this area, there is no spots. But once you find there is no spots when you do analysis of this CH2 and this CH2, no spots, in this case, that can give you a hint. It is this molecule. But that's not a strong evidence. That can only help you to tell it might be this, not confirmed. If you want to confirm is this one, you need to find other evidence. You need to see the spots. Without seeing the spots, you cannot say too much, right? Now we analyzed before. Once is for this radioisomer, we will see this CH2 should show correlation with this one, this CH, right? Which is a doublet. Now for this distereotopic proton pair, they should show correlation with this CH. This is another doublet, right? Here there are two doublets. One is here, one is here. This one, this two, and now for this is this CH2, this two distereotopic proton pair is this one. I still draw lines here. Now you draw. You see for this CH2, that's this one. This CH2 here, these spots, that's on diagonal, and show correlation with this. Here is a cross peak, right? Clearly you can see it's a red dot. It's a cross peak. Then you draw one line, it goes to lower doublets of the sp2ch. That means this CH2 have correlation with one of these doublets, right? It confirms this part. But now we see the other part. This distereotopic proton pair should show correlation with another doublet. That should be this one, right? It cannot be the same doublet. This one should correlation with one doublet. This one should show correlation with another doublet. Now this CH2 here show correlation with the lower doublets with the cross peak here. Now those two CH should do correlation with the top CH2, the top doublets, right? Now you draw another line. Now this is in blue. This one spots the other spots. You draw another line. You see here, there are two spots. That means this distereotopic proton pair, that's this CH2, has correlation with this doublets. Now it's confirmed is this radioisomer. At the same time, you can tell this doublets with a higher chemical shift, right? That's this one with higher chemical shift, the same as this. It should correlation with this CH2, right? That means the doublets with higher chemical shift is this CH, right? Then the doublets, this doublets, that's here, it's this CH. Through this nosy analysis, you can also assign this proton and this proton, right? Before from the 1D NMR, both are doublets, but you cannot tell which one is which. Now after nosy analysis, we can tell this has correlation with this CH. That means this one is this doublets. This one is this doublets. Now this one is triplet for sure is here. Now we assign all this. Now we tell, okay, this spectrum belongs to this one. We just go to the two spectrum in the beginning. You see, this is two doublets squeezed together. That's this one. This two, that's the second nosy we analyzed. That's this one. Right? Now with nosy, we can tell those two molecules apart. We can tell which one is which now. This is one thing. One example of nosy. And then we give another example. That's this spectrum. They also bring one sample. They say it's maybe one of this 4 radioisomer. It gives this spectrum. Can you tell which molecule is this one? Actually, for HSA, they take our graduates, and last year one of my students before find a job there, and they come back for animal training. And for this one, it's those 4 molecules, possibly this 4. But first we do analysis on 1D to see, just based on 1D, can we confirm or exclude 1 or 2 possibility, right? Most easy one is here. You can see the aromatic part. We have 1, 2, 3, 4. Actually here 1, 2, 3, 4. We have 4 sp2ch in the aromatic region, right? They have 2 singlets, 2 doublets. Of course, this one is a doublet of doublet. As I mentioned before, for small coupling constants, you just remove that one. That's due to the long-range coupling. Now you see this is a doublet, this is another doublet, this is a singlet, this is a singlet. That means for the aromatic CH, what?
Can you repeat that just now, the assignment?
Which one? This is the doublet. Because this is the doublet of doublets. You can see from those, but you can see this, they have 1 large coupling constant, 1 small one. The small one, that's due to the long range coupling, right? Then you consider this as a doublet. Now this one is a singlet, right? This is two overlap. On the left side is a singlet because you see these three lines. The left one is a little bit broad, and these two, they are sharp. You can also see from here, for these four numbers, the left one from the left, the first one and the third one, the difference is 0.017. Now here, for those two sharp one, you also for the two right number you minus each other, you get 0.017. Both is 0.017. This spectrum was recorded with 400 megahertz spectrum. That means this doublet and this doublet, they couple to each other. They have a coupling constant of 6.8 hertz. Because for this, after this module, you should readily calculate those numbers. You look at those, you can calculate. This is the easy way you can tell this doublet talk to this doublet, right? Now, for aromatic parts, we have two doublets, two singlets. We analyze those four molecules to see if we are lucky or not. If we are lucky, we may exclude one or two. Now we analyze the first one. The first one is this four position doesn't couple to anything. It's one singlet. 6 and 7, this CH next to each other. Either one will give a doublet. And this is a discrete CH. It's a singlet. That means in this case, the first molecule, they have two singlets, two doublets. Possibly, they can have this spectrum. Right? Now the second one we see here it's a singlet, right? Now for this 1, 2, 3 substitute phenyl group, you will see this CH and this CH will be doublet. The middle one will be triplet or doublet of doublet. In this case, we can tell it's not this one, cannot be this. Now the third one. The third one is very similar to the first one, just the methoxy is in different position. You can see this is a singlet, this is a singlet. These two should be two doublets because they're next to each other. Sorry, maybe you cannot see. Right? Possibly the third one is also possible. Now we look at the fourth one. The fourth one is very similar to the second one. You expect one singlet here, one doublet here, one doublet here. This one should be triplet, right? That means this is not possible. This is not possible either. That means for this spectrum, they can be either the first one or the third one. Now we need to find out, is the first one or third one? Just based on the 1D NMR, we cannot tell. But as I said, we can use noisy spectrum. We do analysis. If it's the first one, for example, if it is the first one, you see this is the ethylene group CH2, this is another CH2, right? For this molecule, this 2CH2 should have correlation with this singlet and this singlet, right? For this molecule, if this is the third one, this CH2 and this CH2 should have correlation with one of this singlet and one of the doublet. Now you find the difference. If it's the first one, this is 2CH2 should see correlation with 2 singlet sp2CH. If it's the third one, this 2CH2 should show correlation with 1 singlet and 1 doublet, right? Now this is how Noddy spectrum looks like it's very messy. It's expected. For noddy, it's most of the case is very messy. Now we look at first we just look at those 1D NMR because we need to find out where is this CH2, where is this CH2, right? Because for aromatic one we analyzed already. But for this ethylene group we haven't identified the peak for them. Now you see this ethylene, this CH2 is a kind of a benzylic. It's just next to a aromatic ring. And this one, CH2, is next to a nitrogen, right? In that case, you will see this is one CH2, this is one CH2, this is one CH2. Because here you see this is one CH3 plus this CH2 is 5 proton. This is 4 proton. Either one is 2, 1. This either one is 2 protons. Right? Now you will see these 3 protons, 3 type of this 2 proton, 2 proton, 2 proton. You will see which one is that methylene group. Right? Normally we expect lower chemical shift for benzylic than the CH2 next to nitrogen, right? That means one of these two will be this kind of benzylic CH2. That's this, one of this little one. But now you need to identify this CH2 and this and this, because this is a CH. This is also a CH. Together, they are CH2, also next to nitrogen. This is a CH2 next to nitrogen. This and this, they are 2 CH next to nitrogen. For those two, this CH has 2 more methyl group. From the knowledge we know from 1D NMR, once they have more substituted CH, they have a higher chemical shift, right? In that case, we can tell this little one is 2CH. One of this is this CH2, right? Because this one, the resolution is not great. Because you can see this one is a kind of isopropyl CH. If you look at it closely, you will can tell this is isopropyl CH. That means those two are this CH2. Now we want to see if these 2 signals has correlation with or 2 doublets or 2 singlets or 1 doublet, 1 singlet. We need to find it out. That's like this. Now we see these 2 little ones, these 2 peaks are this ethylene group. We draw 2 lines. Now we look at those part. This part is this is a doublet. These 4 peaks. From the top is doublet, singlet, doublet, and a singlet. Because you can see from doublet, singlet, doublet, singlet. That's from right side to the left. So on this dimension is from top to the bottom is a doublet, singlet, doublet, singlet. Now we know where is those 2 ethylene group, and we draw lines. One line, you can see here there are 2 spots that correlate to this singlet. At least we see this CH2, those ethylene group show correlation with 1 singlet already. Now we want to check. They don't have any correlation here in this area with the top doublets, right? Now we want to find out for those two, one doublet, one singlet, they have a correlation from here. If you draw, you cannot tell, right? Because this squeezed together is like this. You cannot tell, but we have the zooming area. You know, this one is the CH2, CH2. CH2, CH2. This is one singlet of aromatic CH. This is another CH of aromatic CH. Then you draw two lines. This is a CH2, CH2. That's this one just rotate 90 degree. You know, this is a CH2, CH2. That's this two. You draw two vertical line, you rotate 90 degree, then you see two horizontal line. This is the CH2, CH2, that's here. Now for this, for correlation with this singlet, from this spectrum we can tell this is the middle one. This is the middle CH, is correlation here. That's this one. But now the thing left is for this doublet and singlet overlap. You see, this part is doublet, this is a singlet. You see here, you can clearly see the middle of this singlet across these two spots. Now, in this case, we can tell this CH2 ethylene group, two methylene group, have correlation with either this doublet, this singlet, and this singlet. Now you know what this molecule is. The ethylene group show correlation with two singlet. This is a singlet, this is a singlet. It's confirmed is this molecule. Now we can tell for this spectrum, it belongs to this molecule, the first molecule. This zooming area is clean. It's very clear. This CH2 has correlation with this one and this one. This is a singlet. This is another singlet. It's confirmed in this molecule. Now it's the 2D noise spectrum is very useful to identify the radioisomer, different radioisomers. And we're still missing something. Maybe no batteries. We're still missing something. That's this is radioisomer. There is one stereoisomer, like the double bond is cis or trans. I will give more information during tutorial. That one is important. I leave it in tutorial. Normally tutorial we didn't talk anything important, but I do. Right? That's why I hope you guys can go to tutorial. Because I don't want you to do bad in your final exam. Right? Everybody wants to do well in your final exam. But you want to get a good result, you need to spend efforts. Otherwise, there's no way you can get. Right? I hope you guys can go to tutorial. Because for this module is spectroscopic analysis. Practice is very important. For the theory, I can spend like 2 hours to finish all the theory. But practice is very important for this module. That's why for the people from HSA, they know the basics, but they don't know how to use the fundamental knowledge they have about NMR to practical or to practices, right? Okay, we have 5 to 10 minutes break. Then we talk about the last one. The last one is not so important, but I do hope you can focus on what I'm talking about.
then you cannot conclude that it is a certain isomer. But if you look at this one, right, he concluded by saying that it's singlet, and then the doublet doesn't have anything. Isn't that contradictory? Yeah, but this you also like cannot conclude, it's okay, fine. I wish you were